as fast as possible. Yeah, so you've got a little preview as we were talking about. You've heard, obviously, been associated with this debate before, but I'm John, and we are going to talk about trapezoids today. Maybe you looked at the QR code already. It'll also be at the end, and it's just these slides, along with slides I'm not showing today, which are form an appendix of sorts as well. So in a second, I'll poll the audience. And these are your options. You can, even though you have thought about this a lot and you have not thought about this very much, you can both be kind of involved in this poll. Option one is, of course, the kind of traditional definition. That is, it's a quadrilateral that has exactly one pair of parallel sides. The others are not parallel. That's what a trapezoid is. The inclusive definition, as it's being called, where a trapezoid is defined as a quadrilateral with at least one pair of parallel sides, leaving open the parallel status of the other two sides. Or you can vote that it's a tie. In a moment, I'll ask for you to register your opinion about that in a second. But let me give you a little bit of background while you think about it here, because you're still forming your opinion. I can tell you're searching your heart. Yeah, so there is actually a lot of history about this in discussion, if you can believe it. Some people want to hear this.
I taught with him.
Oh yeah, Will Rose. I was just texting with him this morning. Yeah, we have been friends at least since 2015. Very, very close friends. And so there has been, even though you might have been insulated from this, there has been a lot of discussion and possibly even some heat around this. So people can get even in contentious debates about this. Right? People have strong opinions about this. People think it's settled, and a lot of people think it's settled in one way or the other. They're not sure. They're not sure which it is, right? And it's possible even to talk about this for a whole hour at an MCTM talk. And yeah, this is, so Will Rose and I, your
Yes.
person you know and I,
Yeah.
we did a few years ago at National Council of Teachers in Mathematics, we did staged a 1 hour debate. And he took one side and I took the other. And this is Dan saying, so we should still be friends afterward, which we are, so that's perfect. So here we are, Will and I, doing an hour-long debate.
That is
And you might not think there's an hour's worth to say about trapezoids, and yet there is. We also cooked up some political campaign style buttons for people to wear and register their opinion on this subject as well.
Well, I'm all about inclusivity, so.
Yeah, exactly, right. Okay, so now I'm going to come back to the poll, and now we have some more people to give a vote. You can register your opinion too. The big question on the table is, what is a trapezoid? Okay, so the vast audience, ready to go, everybody. How many people are voting for one? The exclusive definition.
So hard.
You're I know, I can tell you're on the fence, big time.
On the fence.
Exactly one pair. Okay, you're on the fence. Maybe you're number 3. You're at number 2. I know. I heard that when you came in. And then maybe you're a number 3. Is that maybe or maybe 1?
Maybe it is a number 3 because I'm really happy gracious right now.
Well, we're going to see why. This is extremely important and relevant. And why everybody should be thinking about trapezoids. I promise.
What is your thought?
Yeah, did you have an opinion too?
Well, I was going to get the T-shirt. They've got the T-shirts with them, whether you're team inclusive or team exclusive.
Yeah.
I can't think of her. I've seen the presentation several
which
times.
one are you?
That's what I'm trying to think. Which one was I going to get? And I want to say the
don't know.
inclusivity because come on, I think
I know, because then you're guilted
So
into picking
again,
number 2.
the thing you have to agree to is that a parallel, if you're a number 2, then you have to agree that a parallelogram is an instance of a trapezoid, right? So in some people want that.
That's cool.
You think that's cool?
Yeah.
A lot of people are with you, exactly. So let's summarize the debate. Let's start with, just from a historical perspective, the status quo, and that's the exclusive definition. It's kind of been the one that's been in the textbooks forever, and that is that it's exactly 1. And every time I'm going to talk about defending that side, I'm going to use a maroon slide so you can know, just so you can keep score. See, this is a slide that's speaking about the exclusive definition. So this is kind of what it's been like all along. But if you're a geometry teacher, then you know that you're untrusting of diagrams. And so technically, if you're an exclusivist, this is not the appropriate diagram. This is. Right? You have to, if you're a person that insists that the other sides be non-parallel, then you would have to kind of show it this way, right?
Correct.
Even though someone might be like, but it's obvious they're not parallel. Well, we don't do that in geometry,
No,
right?
you can't assume.
If you're a traditionalist, if you're an exclusive trapezoid person, then that gives rise to this quadrilateral quadrilateral hierarchy, which is found in many, many textbooks, some of which you've taught out of our curriculums. You'll find this image online, this kind of thing. Where trapezoids then enjoy their own island, their own area, kind of, they aren't related intimately to these at all. They're kind of their own thing.
Yes.
Yeah, so that's kind of the traditional hierarchy. And honestly, this is honestly an argument in itself. It's like, this is kind of the conservative argument. It's like, if you come up against like a fence randomly in a field, before you tear it down, you should like ask what its merits are. Like, why is it there? And the same thing is true for the trapezoid definition. Like, maybe there's a reason that it's always been this way, right?
Yeah.
And there are, but people maybe haven't thought it all the way through. It does, at the very least, seem to work, right? Like, there are all the proofs you do around trapezoids seem to work
Yes.
just fine. And if it isn't broken, why fix it, right? Like, there's nothing to fix. It works really well for all those proofs.
Has it been a tradition worldwide though? Or is it just?
Yeah, pretty much always. In fact, historically, it's been true all the way since Euclid, who defined every single quadrilateral in an exclusive way, actually, including rectangles. Like, squares are not rectangles, to Euclid even. Okay, so now switching to the inclusive definition, and this is the kind of the classic argument here, that since it's now defining it with this phrase at least, that means that as you, kind of in this classic way, as you slide around, there's my dynamic version of it. I guess I forgot that that was linked. Apologize. Let's see, how do I?
It's okay.
There we go. Yeah, as I slide this around, there's like this moment at which it becomes a parallelogram, and in the same exact spirit that if you're sliding around a rectangle and like momentarily it becomes a square, you wouldn't be like, right then, it's not a rectangle anymore. You would be like, yeah, that's a rectangle too. That's the spirit in which the inclusivists would defend this too. They'd be like, surely, as we slide this around, there's that moment it becomes a parallelogram. Surely it doesn't stop being a trapezoid, right? They would say, like, slam dunk, right? And there's more arguments to be made too. This inclusive definition gives rise to this hierarchy, which brings the trapezoid into this family, where the parallelogram, and in fact not just the parallelogram, but obviously like even the square and the rhombus are instances of the trapezoid. They are children, and the trapezoid is the parent. You can see there's some association over here with an isosceles trapezoid too, coming into that. So that's the kind of inclusive hierarchy. The thing that's appealing about this is this kind of thing, right? This is the advantage of an inclusive approach, is that, for example, things that are true about trapezoids, if you can think of facts you know about trapezoids, then are those also true about squares and a parallelogram? And the answer is yeah, for the cases maybe that you can think of them. So for example, here's the area formula for a trapezoid, and if both bases happen to be the same, then you get the area of a parallelogram. So this kind of, doesn't this show, the inclusivist would say, doesn't this kind of show that we shouldn't exclude parallelograms from the trapezoid? Here's a case where the area formula kind of works. That's one small piece of evidence. All right, we're still on a blue slide here. So let's talk about how mathematicians like to leave things open in terms of their definitions. They like to have general things that kind of encompass other things. So here's the quiz. Which of these is a trapezoid? And if you've been kind of tracking, then your first response should be, before you even answer this question, you should say, under what definition, right? Okay, so yeah, so if you're answering for the inclusive definition, absolutely, the answer is like this one, and also all of these, yeah. Okay, so then what about, yeah, because even the square is like an instance of parallelogram, or of a trapezoid. Okay, so then what about, let's answer it again for the exclusivist. The exclusivist would say, well, no to these, right? They would say, I guess, they would say like, those are the only trapezoids there. But actually, if you take what I said to heart from earlier, the answer is in fact none of them that can you be sure of as an exclusivist. Like this one actually looks questionable there, right? I don't know, it might be a parallelogram. And this one, even though I think it's kind of not a parallelogram, you still aren't sure because they're not marked, you know. Right. So an exclusivist might have to bite the bullet and then say none of them, I can't be sure that they're all trapezoids, and so that they're all not trapezoids. And this gives rise to like this idea that we kind of love. We love these kinds of diagrams, like what's an integer? Well, it's an instance of a rational number, right? Which is an instance of a real number. And mathematicians like this kind of leaving definitions intentionally underspecified so that they can be inclusive. Like this is one of the hallmarks of the generalization that we think of as being mathematics. Okay, back to the exclusive definition, because by now it's kind of like, oh, we can just walk out, right? Like the inclusive side wins. So how could there be any strong merits on the exclusive side? So let's return to that, because there's a big elephant in the room that I'm pretty sure most inclusivists just haven't addressed. And so we're gonna get into that right now. Let's recall the definition of isosceles trapezoid. Now, isosceles literally means, from the Greek, like two equal legs, right? And so everyone's happy with that definition of isosceles trapezoid. In fact, we can do some excellent reasoning about this. So for example, here's a sufficient condition, as you know, please.
So
Yeah.
ISO means same, right? It doesn't mean two.
Yeah, the same size. Yeah,
same
same size. Yeah.
Okay.
Yeah, the same length, right? But you'll see why that's a little problematic in a minute. Okay, so let's do a quick proof from the exclusive camp that would appear like in any geometry textbook of old. Here it goes, right? The thing we're proving is that it's sufficient to prove this is an isosceles trapezoid if we know the base angles are equal. Let's prove that that's true. So the way this proof might go is we extend the legs until they meet, and since the base angles are equal, that gives us that this is, and both these are, this is isosceles and this is an isosceles triangle, right?
Yeah.
And because, so we're making use of that fact from isosceles triangles. And then by segment subtraction, if this is equal, these two are equal, and these two are equal, then it follows that the legs must be equal. And we're done, right? That's kind of the way that this goes. But there's something there's the last animation. And so therefore these are here. But there's something so critical that we need to make sure we don't miss in the proof. What piece? I'm gonna highlight a phrase. Yeah, there's something critical in the first step. Do you see it? Because this is,
How do you know that they will intersect?
yeah, this phrase right here, notice that the fact that we're using the exclusive definition is not kind of peripheral information. It's in fact critical to the success of this proof. If this is an inclusive trapezoid where these might not meet, then this proof fails.
Right.
Right? Okay, so that's an interesting point to make, that this is not just like on the periphery. This exclusiveness is actually like used in a central way in not just this, but almost all proofs about trapezoids. So this presents a bit of a snag for the inclusivist, because let me just go back for a second. What is the definition of an isosceles trapezoid? Well, if it's the two legs are equal, then do you see what that means? It means that a parallelogram is an instance of an isosceles trapezoid. And that is, I think, a bridge too far. That's too much of a bullet for even an inclusive, hardcore inclusive trapezoid person to bite, right? They don't want to be like, no, that's not really what we meant. Like, that's not an isosceles trapezoid, because all sorts of things we want to be true about isosceles trapezoids would fail. For example, we always think of an isosceles trapezoid as kind of looking like this and having equal base angles. You'd have to discard that. You know, all those things you'd have to discard. Things that we want to have be true about isosceles trapezoid. So here's one way that maybe an inclusivist might fix this. They might be like, okay, well, you're right. So what I'll do is I'll redefine an isosceles trapezoid. Here's my new definition. This is kind of what we always meant, isn't it? It's a trapezoid that doesn't necessarily have equal base angles. It does, but that's a consequence of this definition. What we have always really meant is like this thing that has like this nice symmetry that we want. It has this midline symmetry. But then of course the question comes quickly following that, like, does that actually work? So let's just try the same proof we just did a minute ago under this new definition as an inclusivist. Let's see how this feels. Same thing, if base angles are congruent, then it is isosceles. That's the same thing we're trying to prove, but of course now we can't use that extend and have the meet argument like we did with the exclusivists. So here's what we'll do. Construct the perpendicular bisector here in yellow of the bottom base DC. That makes this perpendicular and these bisected. Now, we get pretty immediately the fact that this is also going to be perpendicular to the other base, AB. Now, we don't know yet that it bisects it, because we haven't reasoned to that yet. But we do know that since these are parallel, it's going to be perpendicular to both. So we get the perpendicularity we want, yay. But we also need to kind of establish that this bisects this as well. But if you make a look at this diagram here, what this yellow line that we just constructed does is it divides us into two quadrilaterals, which we can now claim are congruent by ASASA. That's a quadrilateral congruence it doesn't always come up in a high school geometry class, but by ASAS reflexively,
Yeah.
SA, right?
Yeah.
We get the two quadrilateral sides are congruent, and therefore, CPCTC,
Yeah.
these sections up here, therefore these must be equal, and that's the bisector, not just the perpendicular bisector of the bottom for D and C, but also for A and B. So that's and therefore, since this is a perpendicular bisector, we have the midline symmetry that defines an isosceles trapezoid. So I don't know what you think about that, but that's kind of how this would have to go. Let me show you another proof though with the inclusive definition. Suppose we want to prove that the diagonals of a trapezoid are congruent. The way this of an isosceles trapezoid are congruent. The way this proof normally goes is like this. You highlight this blue triangle, and then you, by SAS, prove that that blue triangle I just highlighted is congruent to this blue triangle. And now you have, by CPCTC, that this diagonal and that diagonal are congruent. That's how that goes. Now, let me back it up for a second here. Notice on the right, another proof that someone might want to do is that the diagonals of a rectangle are congruent.
Right.
And notice that that proof goes
Same thing.
the exact same way, right? Okay, so look over here, we got highlight blue triangle, and then draw an inference about the fact that the two, it's the same proof. And the inclusivist loves that, because this is the same, this is just a special case of this if these happen to have been parallel, right? So an inclusivist loves this. We're a huge fan of this, because you have to, if you're an exclusivist, you would have to do this proof and this proof. And yet they're the same proof, an inclusivist would say. Like, that's a waste of our time. So that's kind of a point for the inclusivist, right? That like we kind of maybe have some efficiencies in our proofs too. All right, going back to the exclusive side, another really strong argument for the exclusive side is the following. And we've already kind of seen this starting to kind of happen a little bit. There is a difference in geometry. I'm not sure we talk about this very much in geometry necessarily, but there are two kinds of relationships that we might talk about in geometry. There's a metric relationship that deals with like size or area or the measurement of something, like the size of an angle or the length of something. Then there's another kind of relationship called an incidence relation, right? That when we draw this line, it intersects between these 2 points, or that point A lies on line B, line A. Point A lies on line L, or something like that. This kind of idea, or that two lines, where is it? Or that two lines intersect. This is like a very fundamental relationship, that like whether two things even have an intersection or not, is an example not necessarily of a metric relationship, but of an incidence relationship. And there's in some sense, that's actually the more fundamental thing that maybe precedes metric relationships, is like two things even meet at all. That's kind of a very fundamental idea. And so notice that if you kind of squish these around, and I know that the sliding argument is very compelling that we gave earlier for the inclusivist, but it's actually quite easy, but it's question begging actually, because it's actually quite easy to make interactive with geometry software exclusive trapezoid. And the way to do it is like this. You build a triangle in your interactive geometry software, and then you cut off the top. And now as you drag it around, you cannot make it a parallelogram because of the way you constructed it. And so the way we kind of buried the lead there, right? By the way I constructed that interactive trapezoid earlier, it was kind of question begging, right? It kind of assumed what I already wanted to have be true.
Right.
Where if there is a way of making a dynamic trapezoid that no matter how much you slide it around, it never will become a parallelogram. It would be by just starting with a triangle.
That's
And-
not isosceles.
Huh?
Starting with the triangle, that's not isosceles.
Well, it could be isosceles too, it doesn't matter, but the point is as you move these points, you'll never get these to meet because they're part of lines that meet, you know.
Oh, sorry.
Yeah, exactly. So is there a way to kind of come together on this? And I think I'm gonna give you 30 seconds to just review the things we've just said here. Here are just silently look it over. Here's my summary of the strongest arguments on both sides. do you think? Strong cases, really, on both sides, you know? And by the way, part of the appendix you have access to, if you look at the whole set of slides, is like a whole set of proofs. I just illustrated one or two, but like really, in order to evaluate the effectiveness of a definition in math in general, you really need to kind of do the work. I think there were a lot of people, as the inclusive definition became popular, they were like, oh, that's really elegant, and we all kind of rushed around this one maybe. But if you haven't actually done the work and been like, does it actually work? Like I think most of the people who are proponents of the inclusive definition perhaps haven't even thought about it deeply enough to recognize the issue with the isosceles trapezoid that I raised. Like you need to do, even that could be like a thing someone hasn't thought about. And that means, you know, we really need to do the work when we're doing the definitions. So that's what my friend Will and I did. When we first started having this debate, we were like, let's sit down and actually do every proof that's traditionally in a geometry textbook, using both definitions, and kind of compare their elegance, right? And does it actually like work? That's how mathematicians decide on definitions. And so we do learn some more general principles about things, not just trapezoids here. That, you know, one thing we could do here is maybe settle the debate by having a name for each, right? You know, like the trapezoid and the trapezium, use the British, you know, or we could say the inclusive or the exclusive, we could like name them both. But this is also a larger principle than just trapezoids. It also is important to say that every definition is necessarily exclusive and inclusive. Every definition provides a dividing line between things that are that thing and things that are not that thing. Otherwise, it's not a definition. And then this is the thing I was just saying, we really need to do the work of following through on the definition to see if it works and is elegant and does what we want. And so definitions are a part of mathematics that are decided on. There's a lot of stuff in math that isn't decided on, most of mathematics, in fact. The theorems, we don't have any choice about whether something ends up being true or not but the definitions are human choices. And that's, I think, something that we can engage our students with, too, that maybe we can even, because they're gonna ask, well, which is it, right? And the answer is, well, actually, I'm so glad you asked. There's actually a fun debate going on in the mathematics community about that. It isn't that cool that math isn't like completely settled, and this is something that they can even be invited to be part of, because, I mean, who can't talk about this? I mean, elementary school students can even enter this debate, which is fun, right? And then they're like, oh, really? Oh, really? Mathematicians haven't had this settled yet? And because, like you said earlier, this is actually not that big a deal. We should be gentle with one another, right? You know, people got really heated about this.
Did they really?
Oh, yeah. People were like, people were like, oh, you're...
So which side did you argue?
Which do you think I argued?
I think you were exclusive.
I know Will, so I'm thinking Will is exclusive.
You don't know him well. I was the
You were
inclusivist,
inclusive.
and
Okay.
I've kind of come around to his side of things a little bit.
How do y'all know each other?
Oh boy, yeah, we go way back. We're actually the same MCPS pledge class. We went to NEO together, and we also have a Richard Montgomery connection too from years ago. But we like talk all the time. Like I just texted him this
What's
morning.
NEO?
Oh, new educator orientation. Like years ago, we came on together as teachers 20 years ago.
That's MCTM.
But yeah, I know him quite well. Yeah, so I have a few other slides I can share with some of those proofs. I have some other like small points I can make, but that's kind of I think you've kind of heard the big case for both sides, and then also some of the implications that we have for.
So you lean now more towards exclusive.
No, I find myself in the middle, squarely in the middle, but I originally was in that debate, I was the inclusivist,
Yeah.
and he was the exclusivist, and we kind of
Yeah.
did a theatrical debate going through them all. And you can see it in all of
So
its
the other
glory.
teacher, is he also in Montgomery County?
Yeah,
Yes.
he's another Montgomery
He's
County
at
teacher.
Blair High School.
Yeah, I don't have what is the time right now, by the way?
It's 2:23.
Oh, good, we're doing okay. So we have a few minutes before we're supposed to get down there at 2:30 for our raffle. Yeah, so definitions are like a hot topic. You know, like so a friend of mine, Christopher Danielson, has written this little children's book called What is a Vehicle? And it has like a picture of like a horse and like a picture of like all kinds of things that are like, is that, kind of asking, even with a child, like what, that's kind of fun,
Yeah.
definitions are fun. But like Vladimir Arnold said, the definitions have a human part behind them, right? Like you're probably motivated to define something in a certain way because you want something out of that definition,
well, and to make
right?
you feel comfortable about what's going on around you.
Yeah, you have like a reason for defining it that way. They don't happen in isolation. So I won't go through all these, but there's like there's a bunch of proofs in these slides that someone could look at with more
That
leisure.
is hilarious.
Done in each way, the exclusive and the inclusive way. So that's kind of in the appendix, if you wanna check out those slides.
I already did.
Oh, yeah, I have it.
Yeah.
Yeah. People talk about the trapezoid rule in calculus as being, but that's not really an argument. Cause like, you might look at that, but then, is that a trapezoid?
I don't even know what I'm looking at.
I know, like, so there's lots of,
The rectangle would still be considered a trapezoid.
Yeah.
yeah, in the inclusive definition, but yeah, under that last one though,
In calculus, you would still.
absolutely, yeah, this is called the trapezoidal rule, so like, yeah, that's a trapezoid, but this is also a trapezoid. This is like bow tie shaped region, and again, I think that's a bridge too far for even most inclusivists, right?
Well, the definition of quadrilateral.
Yeah, right, usually that excludes things that have self-intersections, absolutely, right. But yeah, you can imagine that like, and there are lots of definitions throughout mathematics that are exclusive. You know, the Archimedean solids really should include the Platonic solids, but usually we don't, right? They're like the 13 of them and not the 5 of those included, for example, you know. There are tons of things. Anyway, so there's, yeah, or like,
Yeah, so what?
yeah, is that a trapezoid?
What would non-Euclidean geometry people say?
Well, that's a very different conversation direction. I mean, the idea, even of, as you know, if you know some things about non-Euclidean geometry, even the notion of parallelism is something that is a deep question in those other forms of geometry, right? The parallel postulate is like Euclid's fifth postulate. The postulate about parallel lines is different in each of those geometries, right? So, yeah, you have other issues that are bigger to deal with if you're doing geometry on a hyperbolic surface or on a sphere or something. Yeah. So do you have any mind changes at all, or shifts even one way or the other, just even a notch or two? What do you think? Yeah, you can kind of see the other side at least a little bit, I don't know.
Wait, what were you?
I was more inclusive.
Oh, you were?
But I guess I can see it. Yeah.
Well, no, I'm not saying that one way or the other, I'm
But
just.
that's like, I would, no, because it doesn't have to be a quadrilateral also, I would
Yeah,
say.
no, I know,
trapezoid
this is just,
quadrilateral.
yeah, the point was made earlier, but, yeah.
Not that inclusive.
Yeah, exactly.
Good, this is awesome, thank you.
Well, thank you guys for hanging out, we gotta go see if we won our raffle downstairs,
Right?
right? Yeah, okay.
Good.
Thanks for being my audience, you guys,
Thank you.
so I have someone here.
That was fun.